Hi, everyone. We're starting chapter 9 today, which is center of mass and linear momentum. And you're like, yes, momentum, one of my favorite chapters. Yeah, it is for the most part. It's actually a really nice chapter. The only thing it involves is we're going to touch a little bit of calculus, particularly when we deal with rockets. That's systems where the mass is changing with respect to time. And there we've got to do a little bit of differentiation, but we'll get to that in a little bit. Today, just center of mass and simple collisions with a touch of three-dimensional motion in it as well. Just a quick reminder, center of mass of a body or a system is the point that moves as if all the mass were concentrated there and all external forces were applied there. So I want to quickly just show you this if I can. Most of you remember this little demo right here, doing this live, where I've got this little bird that a student gave me, and its center of mass is directly above this beak, even though it looks like it shouldn't be. Because the wings sort of extend outward like this, its center of mass is right below the beak, and because of it, it balances there. The force of gravity is acting right at that point, which is just downright cool. The same thing's true if you throw a bat or an object like this. The center of mass, if it's that little black point, will rotate around that point. And you could balance the bat as well if you could put it horizontally and balance or put your finger right here below this point, it would balance. I've got this really cute video here from YouTube where you'll see the bat spinning around one point. I love the way he just sort of throws it and then spins it and catches it. It actually gets better here towards the end. I don't know, I think I can jump forward. I can't. I guess he's got to make sure no one else is nearby. But you'll watch here, and it always spins around the same point all the time. For people, the center of mass, if you remember, is right around, or when you're born, it's right behind your belly button. But as you grow older, for guys, it tends to move up a few centimeters. For ladies, it moves down a few centimeters from that. Here it goes. He's going to do a bunch of times in a row now. Get ready for it. It's kind of fun. I'm always amazed he catches it each time. Dink. 1, 2, 3, and I think a fourth time. Whoa. Please do not try this at home with any object. You'll probably hurt yourself. How do you find the center of mass of an object? You choose an arbitrary reference point and you measure the position of each of the masses. Whoa, sorry, went backwards by mistake. For example, this mass right here, you just take m1 times the distance it's away from that pivot or that arbitrary starting point, x1, plus the second mass, which in this case is m2, times how far it's away from the starting point, which is x2. Divide that by the total amount of mass, and it'll tell you the distance from your starting point to the center of mass. So in this case, the center of mass of the system would be this distance, which you calculated from this fraction, and that's it. If you've got a more massive object and a less massive object, the center of mass will be closer to the more massive thing. Again, it's sort of like a weighted average. If you have two equal masses, it should be right in the center of those two. It also works in more than just one dimension. You can work in 3 dimensions. How do you do it in 3 dimensions? Well, if you're looking for the x position of the center of mass, it's 1 over the total mass times each mass times its x position. If you're looking for the y position of the center mass, 1 over the total mass times m, each mass times its y position. And the z would be just 1 over the total mass times the sum of each mass times its z position. Let me give you a quick example. Here's just in 2 dimensions. Where's the center of mass located for this system? Well, let's first of all do it in terms of x. In this case, taking each mass, in this case the 3 kilograms is 0 in the terms of its x position, so 3 times 0, plus 8 times 1, plus 4 times 2 gives us 16. Dividing that by the total mass, which in this case 3 plus 7, or plus 4 is 7, plus 8 is 15, it tells us that the center of mass is, oh gracious goodness, 1 and 1/15 meters over in the x position. In other words, right about here in terms of x. Doing the same thing with y, that 3 kilogram object is 0 in the y position. The 8 kilogram object is 2 meters up in the y position. The 4 kilogram object is 1 meter up. Gives us 20 divided by 15. We find out that this one is 4/3 of a meter in the y direction. So 1 1/3 roughly here. And so where's the center of mass of this two-dimensional system? It should be right about here. Sorry, I can't quite draw. I was trying to put an asterisk, but you get the idea. Oh, there it is, 1.1. Yeah, so I did pretty good. You can do the same thing in 3 dimensions, except in this case, you're going to be working with, for solids, you've got to actually figure out each little chunk of mass dm and how far it's away from an arbitrary starting point, in this case, the origin. If you added those all up, basically integrated them, you could solve it. One way of solving for dm is taking the density, that's the mass per unit volume, times dv, the volume of that little cube I have right here. And again, remember that you could rewrite the rho, the density, as mass per, the total mass divided by the total volume times dv, where dv is that mass of that little tiny cube you see there. I want to give you some quick examples, and some of you might remember this from last year, but at the time your calculus might not have been so good. So where's the center of mass of a uniform rod or meter stick of mass capital M and length capital L? Well, first of all, what you're going to do is we've got to figure out what the dm little piece is here. So I'm going to take a small chunk of it over here that I've got shaded red. I'm going to say that's some distance x away from the starting point. I'm going to make this end over here my starting point. And again, remember the whole length of this thing is L. See how straight I can draw my line. Whoosh. And I'm going to say that this is dx wide. And it has some mass dm. Now we can actually use the equation. The problem is I have to figure out what this dm part here is. Well, so what is dm? And what I can do is simply treat it as a fraction. We know the total mass of this rod is m. So what fraction of the mass is in this red shaded area? Well, if dx is the width of this piece here, and L is the entire length of the thing here, you might be able to recognize, oh, wait a second, the fraction that this red area represents would be dx over L. That's the fraction of the entire rod that I have, times its total mass should tell me what fraction of the mass is in this shaded area, dm. Once I have that, I can stick that in for dm in this equation. So I'm replacing dm with this whole spiel. So this goes in there in place of dm. And now I can actually solve this integral. Oh, what are my limits of integration? I'm going to integrate from 0 here all the way all the way to L, which is the length of this thing. Yes, I could have also done half of L and then doubled it, but let's just go for the whole length this time. Just simplifying a little bit, m's cancel. And I can move L, which is a constant up front. So 1 over L times, that's supposed to be a capital up there, forgive me, integral of x dot dx, which of course is just x squared over 2. So this integral becomes x squared over 2L. My limits of integration, 0 to L, this time I've got it the right L. Plugging in my limits, that minus that, just gives me L over 2. In other words, the center of mass of this thing is the total distance of L over 2 from that end. And you're like, yeah, I knew that before you even started. I know. I wanted to do something really simple first before I gave you something a little bit more interesting. So take a look at this next one. Here's a uniform cone of mass m, height h, and base radius r. And my question is where is the center of mass of this thing? Now, this time it's not obvious. It's like, whoa, wait, closer to the bottom than to the top? Yeah, but where? So what I'm going to do here is the same sort of thing I did before with the meter stick, except in this case, I'm going to take a little slice, I don't know what else to describe it, of my cone, And what I'm going to do is say it's some distance x from the top. I could have measured x from the bottom, but trust me, this actually makes it a little bit easier. And I'm going to say it's dx thick. Same kind of thing, since x is my distance this way, this becomes dx thick this way. Some very tiny thickness. And it's going to have some mass dm. And again, my question is of what in the world is dm equal to? Well, in this case, last time I could take the fraction of the length compared to the whole length. To figure out the mass of this thing here, I've got to figure out its volume, which I'm going to call dv, compared to the entire volume of this cone. So here's my fraction of the entire volume that I have. Now, before you get going on this one, I had to figure out the volume of this piece here. I'm going to define a new variable, capital R, which is the radius, and I know it should be right from the center over, which is the radius of this little shape that I'm pulling out of here. Yes, I realize this bottom one should have a bigger radius, but again, remember, we're letting dx shrink to 0 when we do the calculus, which means basically the top and bottom have the same or approach the same radius, capital R. Why capital R? Because they use small r down here. I wish they had used big R here so I could use small r here, but it's okay. But now I can actually do some similar triangles. Take a look at this. The angle here, up on top here, these are two similar triangles. This big triangle here with h and small r is similar to this triangle formed with x and capital R, which means I can write this. First of all, do you see this? Capital R is to small r as x is to h, since these are similar triangles. And I'm going to use that idea in just a second. Now, so what about this? So what is the volume of my red shaded area? Well, it's going to be the area of this top disk, which is this piece right here, which is pi capital R squared, times the thickness. And you're like, wait, that's like, it's not a cylinder. Yeah, I know, but dx, remember, shrinks to 0. Over the volume, the entire volume. And if you don't remember the volume of a regular cone, it's just 1/3 base times height. So 1/3 the base of this pi small r squared times h, all times the mass. Now the plug-in goes. So now if you simplify this equation down, you get this. But we've got capital R in here, and R is going to change as we work our way down. Remember, we're going to basically do a bunch of different slices at different heights. And R, this part here, is going to keep changing as we move down this thing. So I need to get rid of R, capital R. Well, if you rearrange this equation, you'll see that capital R is equal to x small r over h. So plugging that in for R, I get this. And then if you simplify it, some nice things happen. Small r actually cancels, small r squared. And I end up just with an h cubed down below here. But 3 total mass x squared dx over h cubed. Now I can go back to this original equation right here and plug in my dm. So now I know this is equal to dm. I can plug that in place of dm down here. So dm becomes this whole thing. M is a constant, 3 is a constant. And capital or small h is a constant, the total height of it. So I can move all of those outside of the integral. The m cancels, and end up with 3 over h cubed times the integral of 0 to all the way down to h of x cubed dot dx. Integrating that, of course, becomes x cubed over 4. So putting that in front of this, I end up with this with limits of h and 0. Plugging in our two limits, that looks like 30 to the 4th power. That's 3 times 0 to the 4th power. I should have put a little multiplication symbol in there, sorry. Or we end up with 3/4 the height. So where's the center of mass of this system? It's 3/4 of the height from the top, or it ends up being h over 4 for the bottom. And that's true for all regular conic cylinders. And it's not intuitively obvious, but you can solve it with calculus, which is pretty doggone cool. what happens, or just real quick on this, we might remember from this last year. So here's our equation for the center of mass. You could have used x instead of r. Rearranging it, you end up with that. If you divide this, or I guess I should say more particularly, take the derivative with respect to time, or divide by time, r becomes velocity. Mass doesn't change with respect to time. And the position of the center of mass becomes the velocity of the center of mass. Taking the derivative with respect to time one more time, you would end up with this. M times the acceleration of the center of mass, velocity divided by time becomes that, and the velocity of each piece becomes that. In other words, what's happening here? This piece right here is the mass times acceleration, or the force acting on each part of a system, or it's the total force acting on the system, which is just F net. So what's going to be true here? F net is equal to the mass times the acceleration of the center of mass. If there's no net force, the center of mass has no acceleration. It has to be a net external force. If there's only internal forces on the system, the center of mass does not accelerate. So here's a quick conceptual check. This is an actual AP Physics 1 exam question, but what you've got here is a student and this raft have the exact same mass. And it's in a swimming pool and there's no water drag, and the student's about to walk to the other end of this thing. So first of all, where's the center of mass of the system? Well, the raft by itself would have a center of mass right here. The person's center of mass is right here. Where's the center of mass of this two things? Since they're equal mass, the center of mass would be right in between here. Where it's equal distance x here, equal distance x here. What's going to be true here? There's no external forces on the system, so the center of mass is going to stay here. It's not going to accelerate. It should remain at 1, 2, 3.5 units over. 1, 2, 3.5. So the center of mass should stay directly above this point. In which of these cases is that true? Well, you'll discover boat center of center of mass, person center of mass here. Nope, nope. And the answer is, oh yeah, this one here. Why? The center of mass of the boat's here, center of mass of the person's here. Center of mass stays exactly where it was because there's no external force. The center of mass does not accelerate. It remains at exactly the same spot. And because they start out at rest, it stays at rest with no change of velocity. This one's a classic one. What happens when a shell explodes? Well, like in a fireworks display, the shell goes up, it explodes into lots of little pieces. The only external force on the system is the force of gravity. So what happens here? That external force was making the center of mass go through projectile motion. What happens when it explodes? The center of mass continues on along the exact same path. You're like, well, wait a second, how can that happen? Well, some pieces fly this way, some pieces fly this way, and even later when it's down here, pieces are been falling this way, falling this way, falling, and the center of mass continues to move along this path at every single point. And that's the same path it would have taken as if it did not explode. The center of mass literally lands where it would have landed if the thing had not exploded. What happens about the pieces of it? Yeah, they end up on both sides here on the ground. But guess what? The center of masses of all these pieces, if you did the calculation, it would still be exactly where that would have landed. Just real quick on this one, you might remember momentum is defined as mass times velocity. If you take the derivative of momentum with respect to time, you get this. Well, you can rewrite that as m doesn't change with respect to time, dv dt, or ma. In other words, d, or the change of momentum with respect to time, is equal to ma, which is, of course, the net force. And this is how Newton actually wrote his second law. He wrote it as the derivative of momentum with respect to time is equal to net force. He did not write F net equals ma, even though that's the way we usually write it in physics. He wrote it in terms of a derivative, which is actually kind of cooler. Yeah, and again there, I'm going to skip by that. If no external force acts on a system of particles, the total linear momentum cannot change. Why? If this is equal to 0, that means that dp, the change of momentum with respect to time, is also equal to 0, which is kind of cool. Here is the classic example. In this case, it's a very bizarre explosion. You launch a shell at 20 meters per second with an angle of 60 degrees, and at the highest point, it explodes exactly into two parts, where the back half of this thing ends up with 0 velocity and it falls straight down. And the other part of it, the front half, goes some other distance. And the question is, well, where do these two pieces land? How do you solve this one? Well, first of all, you ask yourself, where would the center of mass land? And it turns out, I'm going to use the old range equation just for speed. You could do a projectile motion one as well, but I was trying to make this as fast as possible. And you'll discover that the center of mass would just continue on its way, and it would land right here, a distance of 35.3 meters away from the starting point, if this is x equals 0. If this is level ground, remember this range equation only works for that. Where would the back half of the shell land? Well, if this is at the very top of its explosion, it should be exactly halfway in between. This should land at 17.7 meters away from this point here. Again, the center of mass should be symmetric, would land here. That's really bad 3, I just realized. And this thing would land then halfway between the starting point and the ending point if it hadn't blown up. Where's the other end of the shell have to land? If the center of mass has to be right here, and this one is 17.7 meters behind this one, where's the other piece of the shell need to land? It needs to land also 17.7 meters on this side, so that we average these two masses, m and m, we get that the center of mass should be right in the middle. So where's it at front half land? It ends 17.7 meters beyond where the center of mass would land, or about 53 meters. Visually, what does that look like? It looks like this. Center of mass lands right there, where it would have landed. That one lands 17.7 meters, directly below the highest point, and this one lands further beyond that point. At every single point, the center of mass continues along the projectile path it would have had if the shell hadn't exploded. There's a piece here, and there's a piece here at every single instant. Graphically, it would sort of look like this. Please note that these numbers down here are not correct for this particular problem, but you kind of visualize it. Here's the path that each one would take. In our case, the blue one would end up going straight down, falling. Why is my pen not drawing? Fragment 1 would have gone straight down, and fragment 2 would have gone even further, but the center of mass line would lie right in between those two. Here's a slightly different problem. What if the boat is more massive than the person? This one's more mathematical. What happens here? Center of mass of the boat's located here. Center of mass of the person is located here. Where's the center of mass of this one? It's going to lie 2/3 of the way towards the boat's center of mass. That's the center of mass of the whole system. And because there's no external forces, that's going to have to stay exactly at the same spot. You can actually calculate the position of that relative to the boat or to the edge of the pier using all the equations we've got here. X times the position of the center of mass times the total mass equals the sum of each little piece of mass times its distance squared. I think I actually calculated on this one. Yeah. The distance center of mass is 2.5 meters. What's going to happen here? That's going to have to remain the same location, and you can calculate very quickly then, given that, where each one of these things are going to have to lie. Why? What's going to happen? When the person gets to the front, I'm going to draw them here, we can call this x, and we know that the distance to the boat center mass is going to be 3 plus x. And you can calculate how far the person's going to be from that, because we know that the distance to the center mass is going to have to stay at 2.5 meters away. What happens if you've got somebody running? In this case, same kind of thing happens here. Momentum beforehand is just the two masses, the mass of the flat car and the person moving at the initial velocity. What happens if they're running? Momentum afterwards is simply the velocity of that minus the velocity of the person, which is the velocity of the thing minus the person's velocity, which ends up being the relative to the ground. And you can solve it very quickly. In most collisions, what do we know has to be true? Just a quick reminder on this one. Newton's third law says that the force on the two objects have to be equal and opposite. In this case, the force of the orange object on the maroon object has to be equal to the force of the maroon object on the orange object. And because the collision occurs for the same amount of time, the impulse, remember impulse, which is equal to the, it would help if I could spell it. Impulse is equal to the change of momentum. Impulse is force times time is equal to delta p. We'll actually come up with a new name for that in just a second, a new variable to represent that. But because the force on this object is equal to the force on this object, and because the time of contact is the same for each one of these, both of these objects have the exact same impulse, which means they both undergo the exact change momentum. That is always true during any collision. Impulses usually are represented with a force versus time graph. The impulse is represented with the area underneath this graph. And we're going to represent impulse with capital J going forward. You're like, why didn't I use capital I? It was originally already used for rotational inertia, so capital J it is. Remember, too many variables, not enough, or too many things to record, not enough variables. So capital J is impulse. You can work this out. For real objects, typically the impulse graph looks something like this, where the force reaches some maximum when they're compressed at a maximum distance. If you've got a function that describes the force, yes, you can integrate it. Otherwise, you can try to estimate it by figuring out a rectangular area by using like the average force and calculating, I think it's like equal to this rectangle, and calculating that, the average force times delta t. This gets to be a little bit interesting. If you've got a bunch of objects running into a target, what do we know has to be true? Well, the change momentum of the projectiles has to be equal to the impulse given the target. Why the change momentum of these or the impulse on these must equal the change of momentum or the impulse on this. So the question is, what's the force on the target, especially if it's kind of locked down to the ground? I don't know if you can see these two things here. We can calculate it real quick. Impulse equals the change of momentum of each one of these projectiles, where n is the number of them. Or you could say n times the mass of each one of these times its delta v would be the impulse. Or more generally, if I just simply say where this m represents the total mass change, it could be the total mass of all these times delta v. But now here's where the interesting part is. We know this has got to be equal to force times time. So the question is, what is the average force? So what times time would give you this? Well, we know it's equal to that. And you can work out very, very quickly then, what's the average force? Well, it would be this quantity here over delta t. If you were solving for this, just move this to the other side. So impulse divided by delta t gives the average force, which gives us this. The average force is the change in the mass, or the mass per unit time, times the delta v. So what happens if they stop? Well, delta v then would just be sorry, I should write this real quick. Delta v, of course, is v final minus v initial. So in this case, delta v would just be 0, which is their final, minus the initial velocity. That's supposed to be a minus, not an equal sign, sorry. What happens if they bounce back? Well, then it gets a little bit more exciting. If they bounce back, delta v, v final minus v initial, would actually end up negative v initial minus v initial. Remember, bouncing back, they would have negative v0 because it's going in the opposite direction, or you end up with negative 2 v0. So you end up with twice as much change in velocity, and you'd end up with twice as much force on our target. So bouncing object off an object actually produces a much larger force. Some real quick examples. I don't think I've solved this one. Hose emits 10 liters of water per second at a velocity of 20 meters per second. What's the force on the hose? In this case, the change in velocity, we'll assume that the water is traveling fairly slowly inside the hose, but when it goes to the nozzle here, it focuses it and gives it a large velocity. We know that the force is just equal to the change in mass over delta T times delta V. So what's in this case? 10 liters of water per second. That's, remember, a liter of water is 10 kilograms. So that's 10 kilograms per second times the change of velocity 20 meters per second gives us a force of 200 newtons, which is why when firemen demonstrate this with small children, they always hold on to it. Why? 200 Newton force on, say, for example, a small, say, 20 kilogram child would tend to accelerate them backwards at 10 meters per second. A fairly large force, or if the child accidentally aimed it downward, this would be enough to lift the 20 kilogram child off the ground. You've seen this before with people who actually skate around or use water hoses to actually lift themselves up or off in the water. What happens if this water hits a target and bounces back? What's the force? Same kind of calculation here. The same rate of water, delta M, delta T is the same. But we end up here as 10 liters of water per 1 second. The change of velocity, it ends up going 10 or 20 meters per second this way, but then bounces back at 1 meter per second. The change in velocity is negative 21. And so we end up with a larger force acting on the object, 210 newtons acting there. Sorry for my bad drawing. What happens if you've got it bouncing off at an angle? Well, here it's not too bad. What we can do is actually calculate the components. There's a component of velocity this way, a component this way. And for this one, a component this way and a component this way. What happens when an object bounces off? Well, the horizontal component actually remains constant. So what's our change in velocity? It's just the change in the, I'll call it the vertical component of the velocity. So what do we solve with here? The change in the horizontal velocity is 0. The change in the vertical velocity is just 2v sine theta, double whatever the component is because it goes from this way to that way. Or you end up in this case, if you plug in your numbers, the impulse in the ball is 1.8 Newton seconds. The average force in the wall is that impulse divided by time, or you end up with a fairly large force of 180 newtons acting on the wall as this ball hits it. Just a quick reminder on this one, completely elastic, kinetic energy and momentum's conserved. Completely inelastic, linear momentum is conserved, but the objects stick together, so kinetic energy is lost. And then a partially elastic, or just called elastic collision, where it's not necessarily complete, momentum's conserved, some kinetic energy is still lost. And how do you calculate this in this case? Please note that in every single case, every single collision, no matter what type, the total linear momentum is always conserved. All right. So what happens if you've got one of these where it's not perfectly? You can do both of these. We did these back in honors or in AP Physics 1. It's no big deal. But what happens if you get this one? Well, then the only way of calculating it is by measuring the impulse, J. And remember, that's going to be equal to the change of momentum of both of the objects. So you can calculate their delta V's and figure out their final velocities. So take a look at this one, which is an old AP Physics C problem. What you've got is this little crate up on top here sliding to the right at 26 meters per second, and it's going to collide with this 5 kilogram object elastically. The key on this problem is notice that it doesn't actually state that it's perfectly elastic. And about half the students who solved it that year, this free response question, assumed that it was. Please don't do that, especially if they give you a force versus time graph like they did down here. And they actually kind of get it a couple of hints as well. They ask you for the total impulse, And they do ask you for the kinetic energy dissipated, which you should say, wait a second, maybe this isn't perfectly elastic. So first of all, finding the total impulse. If we look at this graph, we need to find the area underneath the curve, and we can split it into a couple triangles and a rectangle. If you look at this triangle, it's 2 tall and 4 wide. That's 8. It's a triangle, so half of that 4. This is 10 to the third, and this is 10 to the minus third. Those two kind of cancel out, which means the impulse on this part right here is 4. Here, this is 2 tall, and it's, let's see, wait a second. Its height is 2. Its width is 2. Yeah, it's also 4. And this one, it's 4 times 2, 8 times 1/2. So it's also 4. So the total impulse here is 12 Newton seconds, which is going to be equal to the change of momentum of each of our two objects. So very quickly here, we can figure out the final velocities of both of these. For the 0.5 kilogram object, we know the impulse is equal to the change of momentum of it. So we've got 12 equals its mass, which is 0.5, times its change of velocity. And you'll discover, of course, that its change in velocity is 24. In this case, when it collides the other one, it's going to lose 24 meters per second. So its final velocity is going to be 2 meters per second, still going in this direction. What about this object? Well, doing the same thing with our 5 kilogram object. We get 12 is equal to 5 times delta V. And if I'm doing my math right, delta V should be 2.4 meters per second. Since it started at rest, it's simply going to be moving at 2.4 meters per second afterwards. If you check the momentum, beforehand it was 26 times 0.5, that's 13. And afterwards, its momentum of this object, this cube, is 1. And the momentum of this one, 2 times 5 is 2.4 times 5. 2 times 5, 10, plus that, 12. Sure enough, momentum beforehand was 13. Momentum afterwards is 1 plus 12, also 13. And remember, momentum has to be conserved. It's a great way to check things. Once we have those all those numbers, it's fairly easy to solve the rest of these. The last part of this is you got to do some projectile motion, calculate where this one's going to hit the floor. You know the height of the table, so you figure out how much time it's going to take to fall. Knowing its velocity, you can figure out how far from the table it's going to land. And this cube, when it gets to the end here, is also going to fall, but it's not going to go fall as far. And you're trying to figure out the last thing is the distance between the two, which is a fairly decent question. Inelastic collisions, let me use this diagram because it's a little bit better. In this case, inelastic collisions, remember, they stick together. In the special case where the second object is at rest initially and they stick together, you can very quickly do the momentum conservation, and you'll discover that the final velocity is just going to be a ratio of the mass of the original object divided by the total mass times the initial velocity. It's just a simple fraction. The other thing I want to mention just real quick here is this. If you know that momentum is equal to the mass times the velocity, pause for a moment. Remember, the velocity of the center mass should actually stay constant. It's just the total momentum divided by the total mass. So in this case, I've got two objects. M1 is in motion. Object 2 over here, M2, is stationary. The center of mass is right here, and notice it's closer to this M2, so M2 must be larger than M1. And it has some velocity. The velocity of center of mass has to stay constant, but as this mass gets closer, the center of mass is moving as well. But its velocity stays constant, and when they collide and stick together, from this moment on, the two objects move with the center of mass, with the same velocity of the center of mass, which it keeps moving at the same speed. So this is like multiple snapshots of the collision with respect to time. We can use that idea. Here's the velocity of center mass has to be conserved. It's equal to total momentum divided by total mass to solve some problems. So here's a perfectly elastic collision problem. You can solve this the old-fashioned way. I'll call it the old-fashioned way, with simultaneous equations. You know that in a perfectly elastic collision, both kinetic and energy and momentum is conserved. Actually, momentum is always conserved. So we can easily write this: mass 10 times velocity 12 plus mass 2 times velocity negative 6. Remember, momentum is a vector quantity. You have to consider it. And then the final velocities of these two, let's call this one v1 and this one v2. I'm going to assume they're going this way. If I guess wrong on these, it just gives me a negative answer when I solve the simultaneous equations. Equals 10 times v1 plus 2 times v2. And then the kinetic energy equations, 1/2 mass times velocity squared plus 1/2 mass times velocity squared equals 1/2 mass velocity squared plus 1/2 mass velocity squared. And if you plug both these into your TI Nspire and solve them simultaneously, that's menu option 3, or press menu, then 371. You can put these both in and come up with the answers. But I want to show you the shortcut that I always use when doing elastic collisions, so you can actually solve these in your head. And the answer is if you look at it from the center, or the velocity, or we calculate the velocity of the center of mass, which is just the total momentum divided by the total mass, which in this case is 9 meters per second. So the center of mass would be closer to the 10 kilogram object. So here's my center of mass. And the center of mass is moving at 9 meters per second, both before and after the collision. Now, why is this so helpful? Well, if you can imagine standing on the center of mass and riding along with it, so if you could somehow sort of sit in that one, what would it look like from this perspective? Well, this ball is moving faster than you are, so it'd be approaching you. This ball is moving from the other side, so it's also approaching you. What would it look like is both of them would approach you at different velocities, collide at your position, and then bounce away. The cool thing about it is the velocity that they approach you before the collision is the velocity that they depart from you after the collision. So in this case, what does that mean? Well, the red ball is going at 12 meters per second. You're moving at 9 meters per second. It's gaining on you by 3 meters per second. So it's approaching you at 3 meters per second before the collision. After the collision, it needs to be moving away from you at 3 meters per second. So you're like, oh, velocity is this way at 3. No, that would make it moving away at 12. It moving this way at 3, moving this way at 9. In reality, what has to happen is it needs to be moving 3 meters per second slower than you are. In other words, 6 meters per second. That way, from your perspective, you're riding along with this. If it's going 6 and you're going 9, it would seem to be receding or falling behind by 3 meters per second. And this turns out the exact answer you would get solving these simultaneous equations. So what about the 9 ball? Well, you're moving this way at 9 meters per second. It's moving this way at 6. It's approaching you at 15 meters per second, the sum of these two numbers. Which means afterwards it needs to be moving away from your reference frame at 15 meters per second, which means it needs to be moving 15 meters per second faster than you're moving. In other words, it has to be moving at, if I can write here, 24 meters per second. And it turns out these are the two answers you would have gotten if you had solved these simultaneously, but doggone it, the center of mass reference frame makes it capable of being solved without a calculator. So let me show you this one real quick. On this one, yes, you could solve it with simultaneous equations, but let me show you the other way. So the center of mass in this case is moving at 10. So I'm just going to draw it in here real quick, moving at 10 meters per second. And in this case, how fast is the billiard ball moving towards you before the collision? The answer is it's moving at 11, you're moving at 10, it's approaching you at 1. How fast is it moving afterwards? The answer is it should be moving 9 meters per second. That's 1 meter per second slower than you are, so it would seem to fall away from you at 1 meter per second. Beforehand, this object's stationary, but you're moving this way at 10, so the red ball seems to be coming towards you. Again, imagine you're sitting on this thing at 10 meters per second, which means afterwards it needs to be seen to be moving away from you at 10 meters per second. You're already moving this way at 10. How fast does it need to move? The answer is 20 meters per second. And voila, those are the same answers you would get if you did the simultaneous equations. In this case, what if you had two boxes sliding, and these are colliding ones with a spring between it? One thing has to be true is conservation of momentum. One of the questions they often ask is, how much will the spring be compressed? Well, it'll happen when the two velocities of the two crates are actually equal to each other. You're like, what? Yeah, if this one's moving faster than this one, well, then the spring's going to be being pressed yet. If this one's moving faster than the other block, then this one's lagging behind and the spring's actually extending. The moment that it's actually the spring is maximum compressed is the instant when they're both briefly moving the same speed. And once you know that, conservation of energy should happen. This is an elastic collision. And you get this. And then doing some algebra real quick, you could actually calculate the compression of the spring, which would be this. Yes, it'd be much easier with numbers. You could plug in the numbers up here and actually calculate numerically all this, and it's probably easy. Perfectly elastic collision in one dimension. In the special case where this second object's stationary, it turns out you can actually solve the simultaneous equations and actually come up with this, or these two things. The final velocity of object 1 after the collision is just equal to this, and the final velocity of object 2 is just equal to that. And it's even possible to solve these simultaneous equations in more general forms. This is ugly. The velocity of object 1 after the collision is given by this huge expression, and the velocity of object 2 after the collision is always given by this. So this is for perfectly elastic collisions. Yes, this always works. And you might ask, well, wait a second, how in the world did they get these two equations from this? And the answer is they actually use the velocity of the center of mass reference frame, the trick we were doing beforehand, but this is with all the algebra. Finally, this, or one of the last ones here. If you haven't done this before, it's actually quite fun. Do not do this at home. If you take a large elastic object and put another object that can bounce off of it on top, you can get the top object to fly off at much higher speeds. In fact, I used to do demos, and I still do, where you can actually take a series of objects, of smaller ones, and you drop these all together. When they hit the floor, this top one takes off at incredibly high speeds. I used to do this demo all the time, but there was one time, some of you know the story already, where if these are not perfectly aligned, this axis, these can actually fly off at random directions. And I had the very tiny super ball up here, really tiny elastic ball, about 1 centimeter in diameter, fly off horizontally and put a perfectly round circular hole through the classroom window. It actually went boop, right through it. And I went, oops, I had to replace the window. But the thing I thought about was what would happen if instead students had gotten in the way of that super ball as it put a hole for the glass. And I thought, nope, never more. I now am very careful when I do this demo. So the question is it possible to choose the mass of the baseball correctly so that when it hits this and this one bounces back, the basketball actually stops and transfers all of its momentum to that one? The answer is, yeah, it is. It turns out if you make this 0.21 kilograms, and you might say, how in the world did you figure that out? Well, I know the basketball bounces back with this velocity. And if I want it to actually come to a stop beforehand, I need to have the center of mass moving with half of that speed. 5.94 over 2 meters per second. So that way, if it approaches it at half that speed, it's going to leave half that speed, which means its final velocity is going to be 0 after the collision. And then to make that center of mass move that, I need the velocity of this thing is going to be going downward at 5 point whatever again. I need to have its mass to be this. Just trust me. You can do the math real quick if you wanted. So what height does the small ball reach if you do that? Well, the velocity of the basketball is 5.94, like I mentioned before. At the time of the collision, the baseball is moving downward at that, while the basketball is moving upward at that. If you calculate the final velocity of the baseball will be that after the collision using center mass reference frame. And it's actually going to fly up to a much greater height than what you started. In other words, yeah, and if you put smaller ball on top of this one, it just keeps amplifying it dramatically. One of my favorite ones is the planetary assist. If you don't already know this, we can't build rockets that can achieve a velocity to actually launch satellites out of our solar system. But yet we did that with Voyager 1 and 2. How in the world did we pull it off? We cheated. We used planetary assist, in other words, slingshot. We took our satellite and took it in orbit really close to a moving planet. And you might say, well, wait a second, how does that work? Well, you can either use the equation up here and do the calculations, but I love doing it from the center of mass reference frame. The mass of Jupiter is about 10 to the 27th, and I made the mass of our satellite about the mass of a large car, 1,000 kilograms. And if you calculate this, you'll discover that the velocity of center of mass is the velocity of Jupiter. Where's the center of mass located for this system? Well, because Jupiter has so much more mass than our satellite, the center of mass is really right at the center of Jupiter. And it's moving with the same velocity as Jupiter is moving, which is 13 kilometers per second. If our satellite's coming in here at 12 kilometers per second, notice how fast, if again from the center of mass reference frame, this is approaching. Center of mass is moving this way at 13, satellite's moving this way at 12. It's approaching each other at 25 kilometers per second. So afterwards, what's the satellite doing? The satellite needs to be moving away from the center of mass at 25 kilometers per second. We're still moving at 13. How fast is it moving? It's got to go 25 kilometers per second faster than that, or it has to be moving at 38 kilometers per second after this interaction, which is the same answer you get down here without all the horrible math. If you do this multiple times with multiple planets, you can get crazy fast speeds. Oops. Just want to briefly introduce two-dimensional collisions, but I don't want to make this lecture too long. What happens here? Momentum before still has to equal momentum afterwards. In this case, what's going to be true here? The momentum initial in the x direction is just this. And so afterwards, it has to equal the momentum of this thing in just the x direction, which if this is theta is going to be cosine, the momentum of this object times the cosine of theta, and just the horizontal component of this one, which is going to be its momentum times that. What has to be true about these two vertical components of momentum? They must be equal and opposite. Why? Because this had no vertical component, the resultant here can't have any vertical, so the sum of these two must add up to 0 in the y direction. So this is the x, and this is the y. All right, we'll come back and pick up some more two-dimensional collisions next time. Have a good night, good luck with the homework, and we'll talk to you soon. Bye.